Welcome to Maths with EJD. In this video, we are still talking about eigenvalues and eigenvectors, and the focus now is on numerical computation of eigenvalues and eigenvectors. And I'll be starting with power method. Interestingly, I've done power method like 2 or 3 videos before now, but I think it's necessary just to attack it in another way. I mean, to look at it in another dimension and to look at it alongside other methods that we'll be looking at. So, I think it would be nice to, itemize some of those methods. Numerical. Okay, let me do it this way. Numerical computation, numerical computation methods. Of course, for eigenvalues and eigenvectors, we have the power method. All right. We have what is known as the inverse iteration method. Inverse iteration method. We also have the QR method. So it's some kind of decomposition. QR method using Gram-Schmidt process. We have the QR method. Then we have there are so many methods, but we are going to just look at maybe 4 or 5 of them. So apart from the QR method, we also have the let me see. We have the just a minute. Yeah, we have the Rayleigh quotient method. Rayleigh quotient method, and so on and so forth. But I think these 4 are the methods I'll be considering in this next set of videos. So we start with the power method. Start with power method, and which it's more like a repetition of what I've done. You know, I think in the past, simply. So let's go for that. Let's talk about the power method once again. Power method. All right. So the power method is an iterative algorithm. Iterative algorithm. Of course, iterative because we have to do iteration 1, iteration 2, and all that, and the values keep converging. The power method is an iterative method, an iterative algorithm rather, used to approximate the largest eigenvalue. Interestingly, this is only for finding the largest eigenvalue and its corresponding eigenvectors and its corresponding eigenvector and its corresponding eigenvector of a matrix. So it means that if you are dealing with a 3 by 3 matrix, which would normally have 3 eigenvalues and 3 eigenvectors, uh, the power method is going to give you the largest of them in terms of absolute value, not minding whether it's positive or negative. So you're going to get the largest eigenvector with its corresponding, the largest eigenvalue with its corresponding eigenvector. Okay, it is especially, it is it is especially useful for large sparse matrices, for large sparse matrices where the exact solution, where the exact solution, or rather where the exact calculation of all eigenvalues is computationally expensive. Imagine that you have a 5 by 5 matrix and you need to find the largest eigenvalue. So instead of going through the pain of getting all the five, that's going to be a very serious one. But with power method, you can just see if all you need is the largest eigenvalue, then the power method just gives that to you without so much stress. So let's look at the steps required in this process. The first thing is you start with an initial vector. Start with an initial vector V naught, which is actually random but non-zero. Random, non-zero. So anyone you choose is fine, but make sure it's non-zero. Okay, it can be 1, 1, it can be 1, 0, it can be anything apart from 0, 0. Then the next is to multiply the matrix, multiply the matrix A by the current vector, VK. That's like you have VK plus 1 to be equal to the matrix A that is given multiplied by the VK that you currently have. So VK plus 1 is the next representation of that. And the next thing is you're going to normalize. So you have VK plus 1 now to be normalized as VK plus 1 all over absolute value of VK plus 1. Okay. I mean, in the previous approach, right, I used the matrix method of normalization. So it's still the same thing, but here we're actually using the norm style, of taking square root and all that. So you have VK plus 1 all over absolute value of VK plus 1. Now, this is done to ensure that the vector doesn't go out of hand. So the next thing is, the step 3 now is to do the estimation eigenvalue eigenvalue approximation eigenvalue approximation. So what's happening here is that once once convergence once convergence is reached, the corresponding eigenvalue the corresponding eigenvalue lambda can be approximated by lambda is approximately, and we're approximating, lambda is approximately VK transpose VK plus 1 divided by VK transpose VK, like that. So that's the expression. So let's take an example right now. Example. So for the matrix, so I'm going to use the same matrix I've been using for the matrix. A equals 4, 1, 2, 3. Okay. So step one, start. Step one, take V naught to be 1, 1 like this. So that means that A V naught is equal to 4, 1, 2, 3 multiplied by 1, 1. That's like 1, 1, 1, 1. Then you have 4, 1, 2, 3. So 1 times 4 is 4. 1 times 1 is 1. So then if you add that, that's 5. Then 1 times 2 is 2. 1 times 3 is 3. 2 plus 3, 5. So A V naught is 5 easily. And the next thing we want to do is to okay, I guess I've mumbled. I've done 2 steps together. Okay, I mean, let's just go. In fact, let me not even worry about the steps so we don't box ourselves in a corner. So take V naught to be 1, 1. That we've done already. So it means and we already have it. So AAV naught just gives us 5, 5. So from there now, we go ahead and normalize. So normalize. Of course, AV naught is not AV naught now is V1. Okay, this is V1. Or I could have just said this is V1, right? Because from the formula, that's what it is. VK plus 1 equals AVK. So normalize V1. Normalize V1. So to normalize V1, it means we have absolute value of V1, and that is the norm of that matrix 5, 5. So, and what that simply means is that we have square root of 5 squared plus 5 squared. That is equal to root 50, and root 50 is 5 root 2. So that is the norm. And that means that V1 itself is going to be 1 over 5 root 2, 1 over 5 root 2 into 5, 5. So if you multiply through by 1 over 5, you are going to have 1 over root 2 into 1, 1. Easy. So we go for that. So that is our V1 now, normalized V1. Okay. So to show that it is normalized, I guess I want to, yeah, that's our V1. Uh, we started with this V1 here, but okay, let me say this, let me use this sign to show that that's what we are going to use for whatever we have. Now, I mean, we haven't done more than one iteration, right? But we can just go ahead and since we've also done this before, then we can just settle for this. So the next thing is to approximate the eigenvalue. Approximate the eigenvalue. That means we have lambda is approximately V1 transpose this should be V naught transpose V1 all over V naught transpose V naught, and that is equal to V naught transpose is 1, 1. Then V1 that we just got is 5, 5, right? 5, 5. Then all over, this is looks like the norm of, so V naught transpose V naught is the same thing as the norm of V naught. Okay. So that is lambda is approximately 1, 1, 5, 5 all over the norm of 1, 1. That is what V naught is. So lambda is, so here now we have 5, 5 multiplied by 1, 1 all over uh square root of 1 squared plus 1 squared. Okay, I mean, I guess that's not the deal. We can just do the matrix thing, right? Let's just focus on the matrix way of doing this. So we have 1, 1, 1, 1 like this. So lambda is approximately 5, 5, 1, 1 all over 1, 1, 1, 1. So lambda is approximately 5 times 1, 5 plus 5 all over 1 times 1, 1 plus 1. So lambda is approximately 10 over 2. 10 over 2, and lambda is equal to 5. Of course, this matrix is particularly not the sparse type. We can get the exact value, which is actually 5 in the first place. So, I mean, we could go ahead and repeat this and try to use the convergence criterion. Of course, the convergence criterion is usually this absolute value. So yeah, absolute value of say lambda k plus 1 minus lambda also, that it is less than a particular epsilon, which is the tolerance limit. We can always do that. But this matrix is a simple one, so we simply know it's 5. So we could just stop there, and especially since I've done it before, right? So we can just conclude then that thus the power method the power method has successfully, so normally we should keep going until we get something reasonable. Power method has successfully approximated the largest eigenvalue as 5 and its corresponding eigenvector, its corresponding eigenvector, that's V, right? As 1, 1. Even if you consider 5, 5, it's still 1, 1. Or 5 over root 2, 5 over root 2, it's still 1, 1 because it's the same thing. So that's how this goes. So with that, we come to the end of this video. Watch out for the next method, which is the inverse iteration method. If you have subscribed, thank you. If you have not, go ahead and do that. Hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful this video is. Let me know if there's a topic you'd like me to teach or a problem you'd like me to solve. Like and share also so that more people can have access to this great content. Bye.